Last time we were talking about chemistry of hormones and how hormones are transported in the blood and then move into cells to cause a response. We've talked about paracrine and endocrine and autocrine. I want to also mention prostaglandins. Prostaglandins are paracrine substances. So these are only going to bind to receptors on cells nearby in the perimeter or in the area. And like hormones, they are released in small amounts. The big difference here is they're not stored in cells. They are made just before they're needed. They will be inactivated pretty quickly, and they can control, like hormones, how the cell responds. So it can stop the cyclic AMP from being produced, that secondary message, or activate it. And this has a lot of effects, such as contracting or relaxing smooth muscle. I think about the smooth muscle in the capillary beds that help with vasodilation. They can stimulate or inhibit different secretory glands. They regulate blood pressure. So they have a lot of effects. They're very similar to hormones, but because they're made as needed and released just after they're made, we call them prostaglandins. Okay. So hormone secretion is highly controlled, and this is usually by negative feedback. So underlying negative feedback, that's usually the answer. And we'll see some hormones that are short-lived, like adrenaline, or last a few days. And remember, they're slower than how the nervous system works, but their effects can last longer than the nervous system. And sometimes a few minutes is much longer than the nervous system, where it's a second or two. We can see some hormones released in the urine, and so one way is through urinalysis. We can test to see what hormones are showing up, and a lot of them are broken down by enzymes from the liver to stop their effects, and that's how we kind of control those hormones. I mentioned negative feedback is usually the answer. So if you would, again, star this is a control mechanism where the rising level of a hormone, so as you have a lot of, let's say, insulin, that's going to lead to a decrease in the hormone. So insulin is going to cause the blood sugar to go down, and if it goes down too much, we're going to stop releasing insulin and actually probably release glucagon to counteract that hormone. A non-hormonal example would be your body temperature. As you get hot, your body responds to the heat by causing something to happen to make you not as hot. For example, vasodilation, causing you to become very red and release the heat from the blood, and of course sweating, evaporative cooling. And then your body temperature goes down. If your body temperature goes too cold, then your body responds to that too and negatively gives feedback to make your body temperature not continue to go down but go back up. So as a hormone is used up, the inhibition will stop and we'll start making the hormone again. And there's three feedback controls of hormone secretion with examples. This is the hypothalamus. So I'll show you some pictures next of, I love pictures because a lot of words scare me, but the hypothalamus, remember, it's going to talk to the anterior pituitary, and the anterior pituitary is going to release hormones that talk to other endocrine glands, and those other endocrine glands are going to talk to specific target cells that have the correct receptor, right? And that's going to cause those cells to do something. Well, a lot of times that endocrine gland that released that hormone that's going to go to the target cells for an effect, that being found in the blood will actually turn off the production of the original hormone in the hypothalamus. Again, I'm going to show you an example of this. Please highlight tropic hormones. These are hormones that act on other glands. So anytime you see the word tropic in a hormone, it's going to talk to another endocrine gland. What do endocrine glands do? They release hormones. So tropic hormones cause more hormones or different hormones to be released. Now, the nervous system works the same way. They stimulate some glands to secrete their hormones, and those hormones or the actions of those hormones will turn the nervous system off. And then changes in the plasma of your blood, for example, like how many ions are there or how much sugar is there. We just mentioned that with the glucagon and the insulin can stimulate the secretion or inhibition of certain hormones. So this is how we normally control things, regulate amount of hormone in the blood or amount how we respond to our environment, both internally and externally. But positive feedback is seen just a few times, not often. And this is where, as your hormone levels rise, it actually leads to an increase in the secretion of that hormone. So a rising level of hormone causes more hormone to be released and more hormone to be released. We see this actually in the birthing process as contractions increasing. One contraction causes the next contraction to be a little bit stronger, which causes the next. That's positive feedback. If we regulated, and it's not highly regulated, but if we did regulate the body temperature with positive feedback, that would be like you getting hot, and instead of sweating, you would get hotter. Like you wouldn't, you would vasodilate, you would vasoconstrict, you'd become blue, and that would make you even hotter and hotter. And so we don't usually do positive feedback. We usually do negative feedback. So negative feedback is usually the answer. So this is what I mean by this. So the hypothalamus is going to release a tropic hormone, some releasing hormone, sometimes an inhibiting hormone, but let's talk about the releasing hormone. So a hypothalamus releases a hormone that tells the anterior pituitary gland to work. Well, that anterior pituitary gland releases hormones. And so that hormone being released causes this hormone release. That's why it's called tropic. Look what this hormone's going to do. It's going to talk to another gland. So this is a tropic hormone also. And that gland releases a hormone, and that hormone's going to actually turn off the anterior pituitary gland. It says, okay, we've got enough of this hormone now. You two systems shut down. And this hormone will move through the blood, find the target cells, and you'll have an action. Now, as this hormone in the blood starts to go down, what will happen? The hypothalamus will turn on, activate the anterior pituitary, and we'll just keep controlling the amount of this hormone that's talking to these target cells for a specific action. The nervous system works very similarly. Excuse me. The nervous system, using neurotransmitters, is going to talk to an endocrine gland. And then the endocrine gland releases a hormone, and the action causes the nervous system to turn off the secretion of neurotransmitters for the endocrine gland. And in your blood plasma, let's say levels of ions change and you need to release more of those ions, it will tell the endocrine gland to release a hormone that talks to cells, and those release those ions, and now your ions are back to normal. And then when they do become back to normal, we'll shut off this changing level of substance. We could use sugar as an example here. Low sugar is going to cause glucagon to be released from the pancreas. And what will that do? That'll talk to muscle cells in the liver to release sugar, and sugar will go into the blood, and the sugar in the blood will be higher, and that will turn off this whole process. So here's an example of another picture of negative feedback, just so that you really understand. If you want, this is normal, this is homeostasis, and you go too high, that stimulus is going to be discovered by receptors, which will talk to the control center, and the endocrine gland will be stopped. And what will happen is the hormone will stop being released, and the hormone level will start to come back down to normal, and the opposite for if it gets too low. And this is what you'll always see with negative feedback. As things get high, your body reacts to make them go down. As things get too low, your body reacts to make them go back up. This could be temperature. This could be amount of sugar in the blood. This could be amount of water in the blood. This could be blood pressure. I mean, this is how we control most things in the body, where we're trying to maintain homeostasis. We're never just flatlined. We're constantly in a fluctuation around that goal amount, if you will. So let's get into some specifics. Let's talk first about the pituitary gland. So we see the pituitary gland at the base of the brain, and it's sitting in this sphenoid bone, in this little cavity called the sella turcica. And it is controlled by the brain, and it's considered part of the nervous system. So it's lying at the base of the brain. We'll see it in just a minute, and I'll show you that sella turcica. It is attached to the hypothalamus by the infundibulum, also called the pituitary stalk, so it's kind of hanging down, and it has two distinct portions. The anterior lobe, which I've already mentioned a lot, releases many tropic hormones, and then the posterior lobe, so one in the front and one in the back. And the two lobes are controlled by different methods. So the hypothalamus is talking to the pituitary gland, but each lobe is being communicated with in a different way, and I'll show you how that is. There is a small intermediate lobe that develops in the fetus, and that helps make the melanocyte stimulating hormone, which causes melanin production, but eventually that lobe gets smaller and other systems take over to control melanin production. So we're at the base of the brain, and if we zoom in on this picture, here's that sphenoid bone, and there's that cavity that the pituitary is sitting in, and right here's that infundibulum, that pituitary stalk hanging really close to this hypothalamus. So here's the thalamus, here's the hypothalamus, and then here's that anterior pituitary and the posterior, the two lobes. Now this one's bigger, and that might help you remember, it's going to release a whole lot of hormones, and this is only going to release 2. So how are those lobes communicated by the hypothalamus? Well, the anterior pituitary lobe is spoken to with releasing hormones. So the hypothalamus is releasing these hormones, these tropic hormones, that are transported to that lobe through capillary bed, and this is a portal system, and we don't see portal systems often. We see them about 3 times in the body, and this is one of them, so it's a big deal. All a portal system is a capillary bed leading to another capillary bed. We see this in the kidney as well. And so usually you think of arteries coming towards capillary beds and veins leaving the capillary beds. But every once in a while, I think 3 times, you have a capillary bed that still has an artery or arterial leaving it to another capillary bed. So make a note on here, a portal system is this where you have a capillary bed leading to a second capillary bed. And so what the anterior lobe does is it secretes hormones in response to these hormones released by the hypothalamus. And each of these releasing hormones that's released by the hypothalamus is going to act on a specific group of cells in that anterior pituitary. And if that cell has the right receptor, it will then release its hormone. The posterior lobe is very different. It's not being spoken to by hormones from the hypothalamus. They're actually being spoken to by nerve impulses that travel through the infundibulum. And so these nerve endings are going to connect to the posterior lobe and release neurotransmitters to cause the secretion of the posterior lobe hormones. So here's a picture. Again, I love pictures. So here you see one capillary bed leading to another capillary bed. So artery coming in and then like another capillary bed. That's very, very weird. So hormones are going to travel from this first capillary bed to the second, and that will communicate to these secretory cells of the anterior pituitary to release their hormones into the blood. But if you look at the posterior lobe, it's not capillary beds. It's actually neurons that are moving through that infundibulum right here, this stalk, and they are innervating with this capillary bed and these glands surrounding it. And so it's this neurotransmission neurosecretory is what they call it, hormones. And this would be tropic hormone. So the hypothalamus, which is an endocrine gland, can control hormone secretion in a 3-step pathway. So we're going to release hormones from the hypothalamus that acts on a specific hormone secreting cell in the anterior pituitary. Remember, if the hypothalamus is releasing hormones, it's talking to anterior pituitary. Because how does it talk to posterior pituitary? Not through hormones, right? Through actual nerves. So if the hypothalamus releases a hormone, it's going to talk to the anterior pituitary. That would be a tropic hormone because it's talking to an endocrine gland. The anterior pituitary will then act on cells in that peripheral endocrine gland and stimulate its own secretion and of another hormone that's going to act on what? Another gland. So another tropic hormone here is released. And this endocrine gland could be a number of different glands. And when these cells, these target cells, bind to this tropic hormone, they're going to release their hormone, which goes all through the body looking for its target cells. And like I said, negative feedback controls these pathways. Usually the final hormone, this one being released, will shut off the anterior and the hypothalamus. We saw that in that picture previously. Here's another picture. So the hypothalamus is releasing the first hormone. It's tropic because it's talking to the anterior pituitary. The anterior pituitary releases a second hormone to talk to a gland, so it's also tropic. And then this gland's going to release a hormone that talks to target cells. So this is the first one that's not tropic, the third hormone. And what does the accumulation of this hormone do? Well, it shuts off both anterior and the hypothalamus. So what will happen if we shut off the hypothalamus, this hormone will stop being made, and this hormone will stop being made, and this hormone will stop being made, and these target cells will stop responding to this information. Sometimes the second hormone itself can start shutting this down through negative feedback. So let's talk about these anterior pituitary hormones. They are your growth hormone, prolactin, thyroid stimulating hormone, ACTH, FSH, and LH. And each of these is released in response to a releasing hormone from the hypothalamus. And they also can be inhibited, okay? But we usually talk about how are they released. And so there's 5 different cells that produce these different hormones. So what are the releasing hormones that are released from the hypothalamus that tell the anterior pituitary to release? Well, the growth hormone released by the anterior pituitary is told to release that growth hormone by growth hormone releasing hormone, GHRH. And the hypothalamus will say, hey, stop releasing that by releasing an inhibiting hormone, GHIH or somatostatin, stops the growth hormone from being released. Well, how do we activate prolactin to be released from the anterior pituitary? Well, the hypothalamus is going to send prolactin inhibiting hormone or prolactin releasing factor. How are we going to control the thyroid stimulating hormone? The thyrotropin, C-tropin, that's like tropic, releasing hormone. Adrenocorticotropic hormone is released because of the corticotropin releasing hormone. So all these releasing hormones you're seeing are released by the hypothalamus, and they cause these other hormones to be released. Same thing for the FSH and the LH. They are released by GnRH. Again, pictures say a lot. So here's this picture. Our hypothalamus is part of our brain, and it releases releasing hormones and inhibiting hormones. All right, so here are some of the releasing hormones. Here's an inhibiting hormone. Here's the releasing hormones. And that travels through the blood in that capillary system, through that portal system, into the anterior pituitary, where it acts on specific cells to release their hormones. So, for example, growth hormone releasing hormone is going to cause the anterior pituitary to release growth hormone. Somatostatin, or growth hormone inhibiting hormone, is another name for somatostatin, will stop GH from being released in the anterior pituitary. These red line, these are the actual capillaries. So just in case you didn't know. So what is growth hormone going to do? It's going to be released through the capillary bed, out through the venules, into veins, and travel through the whole body. And it's going to tell the bones to grow, the muscles to grow, and the fat to grow. Prolactin inhibiting hormone is released by the hypothalamus through that portal system to the anterior pituitary, which it tells to stop releasing prolactin. If you stop inhibiting it, prolactin will be released, and that will cause the mammary glands to start producing milk. And so you can see these tropin hormones, that just means they're tropic. That means they're going to act on another gland. And guess what? Not this one, but another endocrine gland. This is an endocrine gland. This is an endocrine gland. These are endocrine glands. So these are all tropic hormones that are going to cause other glands to release hormones. So what is the function of growth hormone? It stimulates cells to enlarge and divide rapidly. So they're going to undergo mitosis and they're going to get bigger. Prolactin promotes milk production in females. We're not sure what the crap it does in males. TSH is going to tell the thyroid, hey, release some other hormones. So it's a tropic hormone, right? Because it's going to cause other hormones to be released, specifically T3 and T4, which are going to help regulate your metabolism. So if you want to write metabolism here, you can. ACTH, adrenocorticotropic hormone. Y'all, these word parts mean something. So they are moving to the adrenal gland, which sits on top of the kidney. It's what part of the adrenal gland? The cortex, the outer part of the adrenal gland. So this is saying go on top of the kidneys, go to the outer part, and you're going to cause more hormones to be released. So ACTH stimulates the secretion of cortisol and other glucocorticoids from the adrenal cortex, another gland, or endocrine gland. FSH, it causes growth and development of the ovarian follicles. These are what houses the eggs in females and encourages sperm production in males. And LH is what causes ovulation in females and helps release sex hormones in both male and female. So that's kind of what they do. So what's the pathway for thyroid hormone secretion? Well, TRH is secreted, thyroid-releasing hormone secreted by the hypothalamus, talks to the anterior pituitary through the portal system. The anterior pituitary secretes the thyroid-stimulating hormone. The thyroid-stimulating hormone travels through the blood and stimulates the thyroid gland and causes it to release thyroid hormones. Those thyroid hormones go through the blood and bind to target cells, and then that hormone will tell these other parts to shut down. The TSH secretion is controlled by two methods. Secretion is controlled to some extent by the level of TRH, so meaning that when this is released, it can shut the release off of itself by negative feedback, but also TSH will shut these down too. And so you see that here. The hypothalamus releases the thyroid releasing hormone, talks to the anterior pituitary. Anterior pituitary releases thyroid stimulating hormone through all the blood, finally meets the thyroid. The thyroid releases its thyroid hormones that talk to the target cells. This thyroid hormone and TSH both will tell the hypothalamus and the anterior pituitary to shut down by negative feedback. So this is good to know, right? What happens if you have a mistake in your GH? Well, hypopituitary dwarfism. Hypo means below. So this is a low, you're not making enough human growth hormone when you're a child. And so your bones, your fat, and your muscles don't grow. And you are considered a dwarf. You have a short stature. Your mental development is fine because you didn't affect the brain. You affected the fat, the muscle, and the bones. What we will learn, or you should have learned, is that as long as that epiphyseal plate is there, you can take HGH and it will cause these bones to grow. But once your epiphyseal plate changes the cartilage to bone and you have that line, you would not want to take any growth hormone. Actually, that would cause acromegaly. So let's skip down to that. Acro means appendages, like an acrobat uses its appendages. Megaly is too big. So this is when you, oopsie daisy, release too much growth hormone. After that epiphyseal ossification, you have the line, the plate's not there anymore. And so you're not going to increase everything, but your bones will thicken and you'll enlarge that part of the body. And so this can enlarge your tongue, your nose, your hands, just one piece of your body. Now, gigantism is it's kind of the opposite of this hypopituitary dwarfism. It's oversecretion of GH during the childhood. So you're going to not have a short stature. You're going to make all your bones, your muscles, and your fat way bigger than it was supposed to. And unfortunately, this is often caused by a tumor pushing on that pituitary gland, causing it to oversecrete. So that was the anterior pituitary. Remember, there was a lot of hormones there: growth hormone, prolactin, TSH, FSH, LH, ACTH. The posterior pituitary only releases 2 hormones. And remember, this is going to be acted on by the hypothalamus, not through hormones, but by the nervous system. So the posterior lobe of the pituitary has nerve fibers from the hypothalamus and neuroglia, support cells, in that anterior lobe. And there's 2 hormones that are produced in the hypothalamus and stored and released by the posterior pituitary gland. So they are transported via the infundibulum. And so that is the ADH, antidiuretic hormone, and oxytocin. So ADH, anti-stop, dia, go through. So stop peeing. This is don't make as much urine hormone. What would happen if you stopped making a lot of urine? Well, you would conserve water in your blood. And so this is going to increase blood pressure, but due to the increasing volume of water, but also ADH will cause vasoconstriction to help increase your blood pressure. So you might do this in response to your blood pressure being too low. Oxytocin, oh my gosh, this hormone, this causes muscle contraction in that uterine wall during childbirth. And if you are a mother like me, woo-wee, oxytocin left a mark on my memory, y'all. It also does help cause contraction of the muscles that allow lactation to occur. They can't figure out what it does in males. It might help with sperm movement, might help with sexual response, but oxytocin is one that, and you might have, if you've gotten induced, you've got the synthetic form of oxytocin called Pitocin. And that actually is one of our examples of positive feedback. As you have smooth muscle contraction in the uterine wall, that causes more oxytocin to be released, which causes more contraction, which causes more release of oxytocin, and back and forth and back and forth and back and forth. So that is your positive feedback example for our hormones. Having trouble talking, sorry. So here is a list of the anterior lobe hormones, what they do, and what controls them in the hypothalamus. The posterior lobe, only the 2, what they do, and how the hypothalamus, remember it's going to be a nervous control, so it's stretch receptors or changes in the blood that will cause changes, those hormones, to be released. Okay, so y'all, the pituitary gland is called the master gland. So write that up here in your notes. This is the master gland. Why? Because it releases so many hormones that talk to other glands. So let's go to the thyroid gland next. Now, the thyroid gland is 2 lobes connected by an isthmus, and this is just below your larynx, your voice box, and it has the ability to move iodine from the blood. And it produces hormones, T3, T4, and calcitonin. We wrote that these have to do with, the thyroid gland has to do with your metabolism. We wrote that down earlier. The thyroid is composed of secretory units called follicles, which are surrounded by a single layer of follicular cells. And then there's colloid, this fluid fills the cavity within. And then outside of the follicle are the extra outside follicular cells. So here's a picture of your thyroid. And here's that huge thyroid cartilage, and the cricoid cartilage would be around here. So this is right here within the larynx. And if you zoom in on a tissue, you'll see it's got these follicles. And these are the follicular cells that are like surrounding this cavity. They call it the colloid. It's filled with this fluid. And then outside of here are these extra follicular cells. So this second layer, if you will, of cells. And here's the isthmus holding the right and the left lobe together. And again, if you look at an actual picture instead of a cartoon, you see this fluid-filled cavity, and then the follicular cells around, and then outside of the follicles are extra follicular cells. So here are the hormones of the thyroid gland, T3, T4, and calcitonin. And T3 and T4 are controlled by the thyroid stimulating hormone of the anterior pituitary. And what do? They control your metabolism for the most part. Calcitonin is unique, and so I would star it because it's a little bit different. What it's going to do is cause calcium to go into bone. So that's how I remember calcitonin. Calcium goes into the bone. So this is when you would lower the blood calcium, because the calcium in the blood is leaving the blood and going into the bone, calcitonin. And so why would you do this? You would be depositing calcium and phosphate ions into the bones to build bone or repair bone or store calcium as bones do. There are some disorders with the thyroid gland, hyperthyroidism and hypothyroidism. And so hyperthyroidism, I believe there's some blanks for you to fill in here. If you have an overactive thyroid, you're going to make lots of T3 and T4, and you're going to have this high metabolic rate. You might have protruding eyes due to this, and a goiter. Graves' disease is when your lymphatic cells, your immune cells, actually attack the receptors on the thyroid membranes, and so they mimic TSH and overstimulate the gland. And so you'll also have protruding eyes and goiter. Hypothyroidism, Hashimoto, and hyperthyroidism infantile, and then hypothyroidism as an adult have different symptoms. And let me just show you. So this is the infantile hypothyroidism. They are going to have lower brain functioning. They did not develop very well. This is Graves' disease, so you can see the protruding eyes and a little bit of a goiter here. And this is they're saying it's a simple goiter, but good gravy. That's awful. So you can tell that thyroid is overactive here. It's too big. Well, the thyroid's found in the throat. The parathyroid, there's usually 4, right? Some people are weirdos and have 3, but usually these are 4. And para, around, are found around or within the thyroid gland. And they're located on the back side, the posterior surface. And they just secrete one hormone, guys, the parathyroid hormone. Easy to remember. So the parathyroid hormone does regulate calcium and phosphates in the blood. And so PTH does the opposite of calcitonin. This is the antagonist. Where calcitonin deposited calcium and phosphates into bone, PTH pulls it out of the bone. And so it will cause those levels in the blood to go up, where calcitonin made the blood levels of calcium phosphates go down. So this does act on the bone, because that's where a lot of our calcium phosphate is stored. Also the kidneys, and what else? Yeah, good stuff. And so we're looking on the back side. This is the posterior view. You see the esophagus right behind the trachea, and here are these 4 parathyroid glands sitting on the thyroid. So here's the parathyroid gland and how calcium absorption occurs. So maybe you eat some food that have calcium in them, and that gets released as cholesterol to tell the intestinal enzymes to change it to vitamin D, and then you have light, which creates those pro-vitamin D to vitamin D. You can also get vitamin D straight from the food, and that all talks to the liver, which talks to the kidneys. Now, here's where the important part is. The PTH stimulates the kidneys, and what that does is cause the active form of vitamin D to be tell whether you can absorb calcium or not. If you have a vitamin D deficiency, you can have rickets, which is malformation of your bones because you can't absorb the calcium without the vitamin D. That's why vitamin D is so important. So here you see the parathyroid hormone, and it releases PTH into the bloodstream, and it talks to bones and kidneys, and then kidneys can talk to the intestines, right, to absorb the calcium into the blood. And this is just a great picture about how PTH stimulates different parts of the body and how negative feedback turns off the parathyroid glands. There are some disorders with the parathyroid gland, so hyper and hypo. Too much parathyroidism, usually caused by a tumor there. If you remove the tumor, it will stop causing too much PTH to be released. And then too much PTH, of course, is going to cause some problems in your bone, and so you'd have to correct that. Hypoparathyroidism, so they're not working, very well. You're going to have muscle cramps and seizures. You won't make a lot of PTH, and so you won't have bones being broken down as much. You'll have a low blood calcium level, and so you have to take get calcium injections and change your diet somewhat. And what would cause this, that they accidentally removed one of your parathyroid glands, or you injured it. Our next hormone and gland, and this will be our last for this lecture, is the adrenal glands, and they call them suprarenal glands because renal means kidney, and these do sit above the kidney, like your supervisor is above you. So suprarenal, above the kidney glands. We'll call them adrenal glands. So they act like a cap, and they do secrete hormones. And the adrenal gland has 2 portions, this outer portion called the cortex, and this more medial portion or middle portion called the medulla. And those are where our different hormones are going to be released. So from the adrenal cortex, that outer portion, it's going to release hormones like aldosterone and cortisol and some sex hormones, where the middle or central portion of the gland is going to release mainly our epinephrine or norepinephrine. We call these epinephrine is just another name for adrenaline, and they call it adrenaline because it's coming from these adrenal glands, the middle of the adrenal glands. There are zones of the adrenal cortex, the glomerulosa, the fasciculata, and the reticularis. We won't test on this, but it's nice to know, and you can see these different layers. So there's a capsule, kind of fibrous capsule surrounding each adrenal gland, and then you have the glomerulosa, fasciculata, and reticularis, and then you've got the medulla, the middle. So this is that outer part, the cortex, and then this is where your epinephrine or epinephrine in the medulla would be made. So how does epinephrine and norepinephrine work? Usually norepinephrine works very similar to epinephrine, but think about adrenaline. What does it do to your heart? It increases your heart rate. It's going to cause vasodilation of your skeletal muscle because you have adrenaline because you are in fear. You're about to fight, right? Somebody or flee them, fight or flight response. And so You want to open the blood vessels to your muscles so you can give them lots of oxygen and nourishment to get you the heck out of there, while you're going to vasoconstrict your skin and your digestive system. You don't really want to think about eating burgers or releasing heat right now. Epinephrine does cause your heart to beat harder and faster, and so your blood pressure is going to go up. Your airways get dilated so that you can breathe more, so that you can get out of here. You're going to activate part of your brainstem, which controls breathing and depth of breathing. You're going to start breaking down glycogen in the liver. So sugar is stored in the glycogen, or as glycogen in the liver, and so you're going to tell the liver to release some of that sugar and raise your blood sugar. So this is very similar to glucagon. And then, of course, it increases your metabolic rate. So all the chemistry in your body is enhanced so that you can respond quickly. So the hormones of the adrenal cortex on the outside are aldosterone, cortisol, and adrenal androgens. So let's look at those. Aldosterone helps regulate the concentration of electrolytes. You conserve sodium and potassium. Cortisol decreases protein synthesis and increases fatty acid release. This stimulates glucose synthesis from your non-carbohydrates. So your low-carb diet or you've got some stress, you're going to release cortisol. Adrenal androgens. Androgens are sex hormones, and these andro means male, so these will work in males or can be converted into estrogens and work for female characteristics. There is something called the renin-angiotensin system, and this helps maintain your blood pressure, and that's really all you need to know about this. This goes into quite a bit of detail, and we're not focusing on that in this course. But aldosterone does promote secretion of your potassium, conservation of your sodium, and water is retained because of osmosis in the kidney. So we'll see this when we study the kidney later. So here is how the kidney is going to cause renin or angiotensin to be changed to angiotensin by renin, and then another enzyme causes another angiotensin to be made, and that stimulates the cortical cells to secrete aldosterone, and aldosterone will act on the kidney to conserve water. The crazy complex. Don't get too lost on this. Just say, wow, I really appreciate my hormones, kidneys, and how this all works. Cortisol is going to be acted on by the brain a lot of times because you are responding to some stress. Now, you want to know about Addison disease. This is an insufficient hormone secretion from your adrenal cortex. So this is going to mess up those electrolytes, those ions that we were talking about controlling. It can have an effect on how you control your glucose, of course, hydration because of those ions, and osmosis. It could increase your skin pigmentation. It can be fatal because you have to have electrolytes for your brain and your muscles to work, as you learned in Anatomy 1. Cushing syndrome is due to a hypersecretion of cortisol, usually because of a tumor or you're making too much adrenocorticotropic releasing hormone tropic hormone in anterior pituitary. But that is going to cause you to kind of waste away, have some atrophy. You will have a lot of blood sugar. You're going to hold water and have some abnormal adipose tissue deposition. We are going to stop there, and our last lecture will be the last one for our endocrine system, and we'll start talking about everybody's favorite gland, the pancreas. So take a break, go get you some food, maybe give yourself an hour of TV and watch the next lecture, or wait till tomorrow if you have time. Hopefully you've started early. Good job if you have.